Let's start by rewriting our expression. So to get the axial displacement, we integrate the axial strain, or that could be called the normal strain in the bar. Either one is okay, because again, all the deformation is being by elongating these line elements. So we are integrating the normal or axial strain along the length of the bar, starting from the left end to the right hand end. So this is one, and now I put a solid box around and ask you to memorize it, and that's true. I do want you to have that one committed to memory. But what happens then if P, A, and E are all constant? So this is going to be a special case that's actually going to dominate most of our analysis. A special case of axial displacement is when P, A, and E are constant. And in that case, the integrand comes outside, and we are left with delta is P over AE times the integral from 0 to L dx. So that's just going to be x evaluated at the limits, and we get the big formula, which is delta is PL over AE. And that is huge. That is a monumentally important formula that you should clearly have committed to memory. So again, memorize, exclamation point. It's very important that you do that. You will see this used countless times, probably during the course of your career, regardless of your background or what you're doing. And it makes a lot of sense. The axial displacement has the force. Clearly, it's a linear response, so it's going to depend linearly on the applied force. By linear, I mean that if you have a delta on the left-hand side, you have P on the right-hand side. Not P squared, not the tangent of P, not the log of P, but P. Then the longer the bar, the larger the axial displacement. That makes total sense. The larger the area, so if you have a material that has a bigger area, it's going to have less displacement. It's inversely proportional to that. And the stiffer the material, the higher the value of the modulus elasticity, the harder it is to deform. So as E goes up, the displacement goes down. So it's a very, very important formula. And it's one, as I mentioned, that we're going to be using many, many times during the course of the semester. So let's dive right in and try an example with this. And we're going to make it at least have a little bit of pizzazz. And so we're going to look at two different bars. So we've got one bar here that's a little bit bigger. And then it is perfectly bonded somehow, welded, adhered, connected to a second bar. Let's make this one a little bit longer, like so. So there are two different bars, and let's call this bar number 1. Let's call this bar number 2. And we're going to put two loads on this. First off, let me identify these locations. Let's call this B. Let's call this point C, and we'll call this point D. I'm leaving off A, capital A, because remember, we're using A for the area, so we don't want to use that up. So I'm going to put two loads on this. A 4-kip load going to the right, located right at D. And then exactly at C, I'm going to put another force going to the left, and that's going to be 10 kips. So this is applied right at the interface. So this is applied right at C. And then the lengths of these bars are going to be, let's give them maybe 1 foot, and let's have this one be 2 feet. So those are the lengths, like so. And let's give the properties of these particular bars. Let's say that bar number 1 has a cross-sectional area of 2 square inches. And the value of the modulus elasticity for this one is 20,000 KSI. Bar 2, that's a little bit smaller. Let's let A be 1 square inch. And let's have the modulus elasticity be 10,000 KSI. Now, the problem statement then is to find the axial displacements at the two kind of critical locations. That's going to be C and D. So find delta at C and delta at D. Now, one thing you have to kind of watch for is when do you get to use PL over AE versus the integral statement. So, question, must we use the integral of P over AE dx? Because what we said was we can only use PL over AE if everything is a constant. But in this case, we don't have to use this. Must we use this? No. Instead, you can use PL over AE but apply it piecewise. So we can use delta is PL over AE applied piecewise. By applied piecewise, we mean that that expression is valid over segment 1, and it's also valid over segment 2. So we have to somehow combine them individually and then add them up, basically. So the delta really means bar stretch. The delta means the total stretch of the bar between 2 points. And so we just have to keep that into account. But you don't have to officially integrate. You can still use PL over AE, but you just do that for each one of your particular segments. Now, I'm going to give you a hint when you confront a problem like this. And the hint is basically to move from the fixed point out. Or the fixed support outward. What do I mean by that? Well, what I mean is you know that the displacement there is 0. So the U is equal to 0 at that location, and it is a good reference point. What I mean by reference point is you can say all of our displacements, if they're going to be absolute, have to be measured from somewhere. So we're going to measure these things from the point where there's no displacement in the bar, because the bar is somehow attached or welded to a fixed support. As you've learned in your statics class, if something is fixed, there is no movement. So we want to start basically from that particular location. All right, so the first thing that we need, and this really is a little bit of a problem for students coming from their statics class, is to find the internal forces in each one. So we need the P in those segments. So let me redraw this very quickly. Let me make that a little bit longer. You'd be amazed at how many people get kind of thrown by just doing the statics. So again, we've got this bar force, that's the 4, and then this is going to be the 10. Notice I moved it, I put the tip of the arrow there, but again, what we're doing is we're assuming it's applied right at that location. One useful trick then is to always make sure that you start with a support force. So when you do your statics, in fact, let's write this up. The key is to do good statics. And you're going to see why that's important, especially with relation to the sign of the axial bar force. So this one is pretty easy. We know that there's a left or right force at the support, and it has to make this particular system be in equilibrium. Well, it doesn't take very long to see that we've got 10 to the left and 4 to the right. So clearly, we have to have a total of 6 going to the right for this to be in static equilibrium. So the reaction is a simple one equation, one unknown. We don't even have to take the time to do it. We want to train ourselves to be a little bit faster. And again, in your career, the faster and the more efficient you can be, the better off you're going to be. So if you can shortcut finding the reaction forces on a problem like this, do it. You don't have to draw free body diagrams, write out the sum of the forces in the X. So we'll write here, no need for a free body diagram, sum of the forces in the X, etc. You can certainly do that, but you've graduated from statics. You now need to make sure that you start to refine your skills and speed things up, because the faster you can be in the execution of your duties as an engineer, then you can spend it on really important stuff, spending time with a difficult client or trying to figure something out where you don't have much experience. So if you can get the reaction force quickly, that would be so much the better. All right, so we have to have a reaction force at the left end and it's going to the right. We've got the force at, so that's this one. We've got the 10 going to the left. We've got the 4 going to the right. Now we're going to do something that may seem a little bit odd, but what we want to do first off is find then first the bar force in that first segment. So we're going to cut that structure. Now here's where we do want to do statics. So now that we've found the reaction, we want to get the statics, and the goal of this is to find the internal values of P. P is not necessarily going to be the applied load. In fact, let's take a look at that for this particular problem. So we've made, sorry about that, we've made one cut. There's our cut number 1. So cut number 1. So I'm going to draw everything then to the left of that cut. So here is our cut, like so. We've got a force of 6, keeps going this way. And now remember what you learned in your statics class. Anytime you make a cut in an axial section, remember you assume tension. So that would be the bar force in segment number 1. I'm going to use that as an ad hoc designation. So this is equal to the internal bar force in bar number 1. And again, I'm going to remind you that we always assume tension. And the reason that you do that is because if you end up with a positive value, positive is tension in an axial bar. If you end up with a negative value, that's going to be compression. Okay, so now we do want to do the sum of the forces in the x is equal to 0, and we have 6 plus P1 is equal to 0. Therefore, P1 is equal to negative 6. So what does that mean? That means that that bar is actually in compression. So hold that thought. I'm going to try to stick to 12.5 minutes. So we are done with the second of our 4 parts for today.